Search latency hides across too many layers. OpenTelemetry tracing shows where FastAPI, retrieval, filters, and reranking actually spend time. You'll walk away with a setup that reveals traced retrieval stages and flags the slowest FastAPI search span. I'm Professor Pi, teaching Search and IR with simple Python. Search systems are a stack. A query hits the API, moves through retrieval, embedding or scoring, filtering, and maybe a re-ranker. When users complain about slowness, it's rarely obvious which step is at fault. Did the database stall? Or is a neural re-ranker chewing CPU? Search Observability with OpenTelemetry makes those layers visible so you can measure and fix the actual bottleneck. Success means sub-second medians, predictable tails, and a small set of repeatable hotspots to tune. In this demo, those hotspots are only a few milliseconds each. At production scale, the pattern is the same: database queries, model calls, and external services. OpenTelemetry works well because it standardizes spans and attributes, so tracing tools show the full call tree without you building a custom profiler. The idea is straightforward. Wrap logical stages in trace spans. Give each span a name and duration. Then emit a summary event on the parent request that calls out the dominant stage. From there, you can search traces for slow requests or build per-stage histograms for offline analysis. We'll build a tiny FastAPI search endpoint that simulates retrieval stages, records spans for each stage, and returns which stage was slowest. That payload makes writing a test trivial. You verify a slow stage and keep the trace context attached to the HTTP request. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we create a baseline tracer and record a single search span so you can see tracing is alive before expanding to stages. This snippet initializes an OpenTelemetry tracer and times a toy search span to set a latency baseline. Debugging slow retrieval gets messy without a clean baseline, so we wire up batch span processor and console span exporter to emit spans you can inspect immediately. The tracer from trace.getTracer creates a search request span, giving you the same context handle every later stage will reuse. Inside that span, we wrap time perf counter around a simulated sleep to mirror a slow endpoint, while still keeping the math deterministic. Capturing the elapsed milliseconds in elapsed ms gives you a stable number to compare when subsequent snippets add richer instrumentation. The printed result confirms the root span exists and surfaces the measured latency so we know tracing is live. Now, we need to break the root span into named stages so we can tell which internal piece is slow. This example layers stage spans onto the tracer so we can pinpoint the slowest retrieval step. Latency tuning falls apart when embedding, vector, and filtering spans live separately. So run search wraps each stage name and delay inside its own start as current span. The loop seeds the pipeline tuple inline, avoiding duplicate configs while still giving us deterministic 6, 14, and 5 millisecond sleeps. Each iteration appends name delay times 1000 to pairs, letting Max pick the worst offender without extra sorting. Because root.setAttribute tags the query text once, downstream telemetry stays readable, even when multiple requests overlap. The print of slow stage and slow ms confirms exactly which span is dominating the request budget. Next, we put that traced logic behind an HTTP boundary, so traces map to real requests. This code instruments a FastAPI search endpoint with OpenTelemetry and returns the slowest stage summary. Without tracing the API boundary, you only see backend spans. So, FastAPI Instrumenter Instrument app ties each request span to the SDK provider we created earlier. The search coroutine stays tiny. It calls run search, unpacks the tuple, and returns a JSON payload that preserves both the span name and milliseconds. Running this under TestClient or Unicorn now yields an automatic server span plus the manual stage spans underneath it. Printing app.router.route/path verifies the path is live, signaling the app is ready for the next layer of instrumentation. To make traces easier to scan, you want a compact hint about the slowest stage directly on the parent span. This snippet wraps the existing search routine to emit an OpenTelemetry event summarizing the slowest span. Debugging route outliers is easier when the parent span logs what mattered. So we keep the original run search as previous run search and decorate its result with an event. The new wrapper calls the previous function, captures the name ms tuple, and uses trace.getCurrentSpan to grab whatever span is active inside FastAPI. Span.addEvent writes a lightweight slowStage.summary record, giving tools like Tempo or Jaeger a quick summary without more nested spans. Because we return the same tuple, downstream code keeps working, while the trace gains extra context. The printed event recorded value confirms the wrapper still reports the correct slow stage after the event fires. Finally, we exercise the endpoint in a test, so tracing flows from client to server and back. This example triggers the I route via TestClient and surfaces the traced slow stage end-to-end. Manually hitting curl won't expose instrumentation details in tests, so TestClient gives us a fully traced request without spinning up Unicorn. The call to client.get travels through the auto-instrumented middleware, which invokes our wrapped run search and logs both the nested spans and the higher level event. We grab the JSON body, split out slow stage and slow ms, and print them so any regression harness can assert the numbers. When the slow stage changes after a tweak, you can diff this structured payload and immediately know a new span reclaimed the latency budget. The printed line confirms the API encodes the slow stage values, proving the trace context flows all the way to the caller. In a real project, you replace the sleep calls with real retrieval, embedding, and reranking steps. The same pattern maps to external model calls, database queries, or feature stores, and lets you decide where to invest optimization effort. Recap. It attaches spans to each logical search stage and emits a parent event summarizing the slowest stage. Use this when you need per request visibility to find hotspots across service boundaries. Caveat: synthetic sleeps are deterministic, but real APIs introduce variability that requires sampling and tail analysis. Next step: run the demo against a larger synthetic corpus and add per stage histograms so you can compare medians and 90th percentiles before and after a fix. If short, practical IR helps, subscribe and watch the IR videos.